I've always really appreciated being able to watch someone's creative process, seeing them be presented with a problem, and then breaking that problem down into the pieces that they are going to need to solve that problem. And I was recently given a question that I thought would be a great candidate for this. And so what I wanted to do is give you insight into how I think about problems and how I take the larger problem I'm given and then turn that into the pieces I'm going to use to solve it. And really my hope is to scale the learning so it's accessible for more people. I have dyslexia, so hearing things is very helpful. Hearing someone work through things helps things stick in my mind better than just necessarily reading a blog post, which are fantastic. But I'm trying to provide the learning experience that's best for everyone. And so I'm hoping to do these more. And if people find them helpful, please let me know. I have found as I've paired with other developers, they have found it very helpful. At least that's what they tell me. Maybe they're just being polite. We'll find out. So here's the first in this series. I'm not quite brave enough to do a full-on live stream, but we'll see where we get. So what problem are we going to work on? Well, recently I was meeting with a friend, online of course, and he was talking to me about a problem that was coming his way, and he was possibly going to consult on it. And he wanted to know if I thought it was a good candidate for mathematical planning. And I thought it was. And I want to take that problem. I'm removing the specific domain so as not to reveal the industry or the specific company, but I'm taking the heart of the problem, and I'm going to show you how I turn that into a mathematical planning problem and then solve it. And this problem is actually pretty simple to state. We have a set of machines that process jobs. At the beginning of the day, we're given a collection of jobs. Jobs have different types. In this case, let us just say, there's a job type A, type B, and type C. And we need to schedule these jobs on these machines. We want the machines to be evenly loaded. Jobs have different sizes, but we want the total amount of load on each machine to be even. And we would like to minimize the number of different job types a machine has to deal with. So ideally, hey, all of type A is on one machine and all of type B is on another machine, all of type C is on another. That would be ideal. Whether that's actually possible or not, we will see. So this kind of problem, this kind of scheduling problem is really common. Right now, we're just going to deal with the most basic version I just explained. In the future, we're going to talk about variations on this and adding complexity and adding different types of constraints and restrictions and scheduling. But this is we're laying the foundation from which we're going to be able to do a whole lot of other really cool stuff. So I want to get that foundation set for you so then we can build all kinds of new cool concepts on top of it. So I'm going to be working in VS Code. I love doing this type of work in VS Code. The INI plugin is amazing. And with F#5 and just being able to use the #r NuGet import is just amazing. So here on my screen, I've created a directory where I'm going to put my F# script in. Just going to right click and say open with code. Opens it up. And then I'm going to do Control-N to create a new file. I'm going to name this, go ahead and save it and give it the name machine allocation example.fsx. So this is what tells it, hey, this is an F# script file. Great. So based on that description I just gave, there's a few types that should immediately jump out to you. The first one, you have machines, you have jobs, and you have job types. So let's start making those pieces for our domain. So I am going to go ahead and say, hey, this is going to require qualified access, and it's the job type equals, I'm going to have an A case, a B case, and a C case. The reason I put this attribute on here, require qualified access, is if I want like an A case of job type, I couldn't just do A. I would have to say job type dot A to make that case. And I find, it really depends on the domain that you're working in, whether this makes sense or not. I find that this sometimes provides clarity, but I'm gonna leave that up to your judgment. I have found it helpful though, kind of forcing that additional clarity. You will find that I will often default to clarity over terseness. And then we have job type. So in this case, I'm going to say, hey, I got a job, and I'm going to say, hey, it's got an ID. And this is just some possibly index. It's just something that uniquely identifies that job. And I'm going to say, well, this job has a job type. And let me get a little more zoomed in here for you, just to make it really easy to see. And I'm also going to have a size. In this case, I'm going to say it's just a float. Making my life easy. Mathematical planning typically likes to think in floats. The math that's down deep underneath that you don't have to see, it's all done in floats. So in this float is a 64-bit float in this case. It's alias for the .NET double. And I actually also like to override the toString because toString gets used a lot in the flips library to name things. And so I like to provide shorter definitions. Now, I'm doing this because I like to make really small, almost like micro domains for formulating the problem. In this case, formulating the model and solving the model. And then I will abstract that all behind some API where you give me a bunch of config information. So I kind of think of this as very allowable, forgivable. You might say, oh, I would never do that in a business domain. That's fair, but this is a very bespoke domain for the purpose of mathematical modeling. So I'm going to change it and say like, hey, job underscore, in this case, I'm going to say this dot ID. And if you haven't seen this syntax yet, this is the string interpolation that came with F#5, and it makes me so happy. It is absurd. It's one of the things where I looked at F strings in Python and string interpolation in C#. I'm like, oh my goodness, we need to get this. It's so good. So the other type it's in our domain is the machine. And again, we're going to have an ID. And the machines, one of the things I forgot to mention in this problem statement is that not all machines are equally capable. Some machines can process any job type. Some machines can only process one job type and combinations within that. So that's one of the things that you have to consider when assigning job. You can't assign a job to a machine that isn't qualified to process that job type. So we're going to say, hey, this has job types. That's a set of job type. Set is one of my favorite collections in F#. It just makes comparisons so easy. So good. And set math is crazy fast. And again, I'm going to override the toString. This dot toString and machine this dot ID. There we go. Now, something I want you to be clear on. I've already worked out this problem and I have code that I'm referencing. And again, it's just because I want to be respectful of your time, but I am going to point out mistakes I made along the way and what my thought process was when I was making these decisions. So again, not quite ready to go completely streaming live, but I'm working my way there. So I've broken down this domain. This is a tiny, tiny little domain. I got the job type, I got the job, and I got machine. I can represent it. Now, in order to kind of, because I can't tell you about the specific problem instance, I'm going to have to generate some data for us to work with. And that's what I'm going to do now. It's going to say like, hey, I'm going to have an array which has each of the job types in it. And then I could just like randomly index into it to create a random job type. And you're going to see how that's useful here in a little bit. Oh, let's clean that up real quick. And so job type A, job type B, job type, I see it. I see what I did. B. Cool. So this is an array. It has all the different job type values in it, in this case, cases. And we will use a random number generator just to like randomly index into this thing to generate random job types for our jobs. I also want to have like random job type sets for our machines, so I can like randomly generate some machines to work with. And so I'm just going to give it some job type sets that it could just randomly sample from. Again, this is all necessary because I can't, show you like the real data, but this is indicative. I'll put it that way. So this is gonna be a set of job types. So what this is saying is like, hey, this is a set of job types. I'm going to be using it to randomly generate machines and fill in this value here. And in this case, the machine is qualified to work on any job type. Great. And I'm going to create a couple other cases where it's job types. I'm going to say like, hey, this one can only do B and C. Because this, with the array slicing here, I'm skipping over the 0 index and I'm saying everything from the 1 index on. So in this case, it would be B and C. And then I also have job types, and I'm gonna kind of do it, but from the other direction, where like, hey, I'm going from the first index of the array up to the 1 index. So this, in this case, it would be job type A and job type B. So this array, I'm going to just use a random number generator, randomly index into it to randomly generate machines. Great. Now, anytime you're generating random data, one of the first things is you need to create a random number generator, but also give it a seed. So important. I'm even thinking of like writing a blog post just about this and making testing and validation deterministic, and you need to control your randomness. And so when we create this random number generator, we give it a seed so that I can run it on my machine. And if you run it on your machine, you should get the same data and the same results. And I can run this again and again and again, and I'm going to generate the same data. Super important. It is a nightmare to debug things when your random numbers are actually not controlled and it's just craziness happening. Not cryptographically safe, but that's not the purpose of what we're doing here. So I'm going to say, hey, how many jobs do we want to work with? Yeah, let's say we have just 20 jobs. I'm gonna keep it small. Let number of machines, and we're gonna say, hey, we're gonna have 5 machines to work with. And I'm gonna say the min job size, because remember, jobs have different sizes. And so I want to put a bounds on that. I say, hey, I'm gonna say the min job size is gonna be 1. And the max job size is going to be 3. Yeah, and there's a reason I'm saying I have them as ints, is because I want to generate job sizes of like 1, 2, or 3. Again, this is kind of coming from the domain. It's like, hey, a job is like 1 hour, 2 hour, or 3 hours. So I'm going to randomly generate integers between 1 and 3 inclusive, and then I'm going to turn them into floats to fill in the size parameter here for the job type. So there we go. And I'm going to create another value here. So this is one of the really important things that, as I was having this discussion about, okay, what's most important about this machine scheduling that you're doing? And there appear to be two competing priorities. One was we want the machines evenly loaded. Okay, fair, that makes sense. At the same time, we want to minimize the number of different jobs a machine has to deal with in a given day. The reason for that is because when there's a changeover from one job type to another, there's a loss there. There's some materials that are wasted. It's really fast, so you don't need to really account for it in terms of time. But there's money that's lost in that situation. So it's ideal if a machine can process the same job type all day. Well, this is interesting because and this is what I really dug into with my friend. Okay, you're telling me that you want the machines evenly loaded, but you also don't want the machines changing job types frequently or at all, ideally. I'm like, well, that's a bit of a challenge. In mathematical planning, you have to choose like what is your actual objective? What is the thing that you're truly trying to achieve? And what are things that are things you want to have versus like this is the most important thing? Because that most important thing is what your objective truly is. It's how you quantify success. And as we dug into this, there's different approaches to this, but the approach I decided to go with is saying like, hey, let's say that minimizing changes between job types is actually the most important thing. So that's going to be our objective function. We want to minimize job type changes on machines. Cool. But I don't want to have a situation where I have a machine with one job and then another machine with 30 jobs. That's not acceptable. So we need to put some kind of constraint on how big of a difference in loading there is across all the machines. And we're going to put a bound on that. We're going to control it, saying like, hey, the difference can only be so much. If it goes outside of that, it's not acceptable. So in this case, we're going to create a constraint which says the difference between the most loaded machine and the least loaded machine has to be less than or equal to some value, some parameter. And that's the parameter that we're going to fill in right now. I'm going to say, hey, that value I'm going to call max work difference. And I'm going to say it's equal to 1.0. In this case, it's saying like, hey, the difference in loading between machines has to be between the most loaded machine and the least loaded machine has to be less than or equal to 1. So that's a pretty tight bound. You don't want to do 0 because jobs, we're going to be generating job sizes and they're 1, 2, or 3. They're discrete values. And so it might not be possible to have every machine with exactly the same amount of work, because if you have like 3 machines and 4 jobs and all the jobs are the same size, like one of those machines has to take that additional job. So right now, we're just going to say this is 1. There will be some follow-up blog posts which like go deeper into this and discuss like edge cases that won't be revealed in here, but will in the future, and how we deal with that. It's the idea of infeasibility, or like there's no valid solution, but we will deal with that in a future day. So now I need some functions for generating some random data. So I have my parameters. Let's do this. So let random job size. I'm going to say that, hey, this is going to take a system.random. And I'm going to say, I want the next value. And this is going to take the min job size as the lower bound and the max job size as the upper bound. And say, I want that back as a float. And the reason I want it back as a float is because mathematical planning, like the solvers down underneath, they think in float, and the flips library thinks in floats. And so your life is going to be easier if you're just working in floats natively. Now, next, in this case, produces an int, and it's going to be between, in this case, 1 and 3. Later, if we wanted to, we could play with these parameters and generate jobs of like a wider range of sizes. But I try to kind of stay relatively close to this domain that my friend was talking about. So we now have a function for generating random job size. I also want to have random job type. RNG system.random, good times, next. Okay, back it up a little bit. So remember, I want to like randomly generate a value and index into the job types. And just to remind you, job types is this array, and it has all the different possible values for job type. So in this case, we're going to say, hey, RNG next from 0 to job types length minus 1. And so this is going to produce a value between 0 and the maximum index in this array. And this is a dense array, thank goodness. So it's just going to randomly index in there and give me a value back. Same thing with random job type set. And this is sampling or choosing a random job type set for when we create machines. So again, random number system.random. Same deal, job type sets. And I want to generate an int that will be in here. So job type sets length plus 1. Why are you angry? Oh, maybe if I spelled things correctly, that would help. Cool. A function for random job size, a function for random job type, and a function from random job type set. Cool. Another convenience, well, I'll get to that later. I'm trying to keep the mental flow going here. Okay, so let's create some jobs, right? We'll create some random jobs. So in this case, we want jobs from 1 to number of jobs. Cool. So that's going to give me a list of ints. I'm going to say, hey, and starting from 1 to the number of jobs. Great. So list.map fun ID. So I'm going to use this int that generated the series as the ID for my jobs. So in this case, ID is equal to ID, and job type is equal to random job type. Using the random number generator, I created above and gave it a seed, and then size would be random job size. All right, cool. We now have some random jobs. Good time. Let's actually run this. I realized we've just been typing for a while and trusting that the compiler gods were with me, and so far they are. Good times. I'm going to put this over here on the right, just so we can kind of see some of our code and what we got going on over here. And now I'm going to generate some jobs. So I created some jobs, and the FSI is kind of printing those out for me. So one of my favorite things to use is this is probably one of my first questions on Stack Overflow back in the day. FSI.show declaration values false, right? So it won't keep printing bunches of stuff out every time we create something. Drives me crazy, especially when you work with really large collections and it can do stuff like this. So I've now turned it off. So I will have to ask it to print stuff out. And now notice when I created the jobs, all this stuff printed out. Now we're going to create some random machines. So machines equal to, again, kind of the same trick. 1, 2, number of machines. I'm going to go list map fun. Again, I'm going to use this integer that I'm generating in this series as the index, the ID field for the machine. So ID, and I'm going to have job types, and again, random job type set, and number generator, random number generator. Now notice I'm going to create machines, and it just says it's a machine list. Good for you. Oh my God, thank you. I don't need all this other information. Good times, good times. So now, where are we at? We've created a tiny domain. We created some functions for generating some random data that is representative. And now we've generated a set of jobs and machines. And now we are at the point to where we can actually start working on our problem, actually formulating the optimization model. Okay, we're back from the intermission. You may have noticed some time has passed. I've shaved. I am now wearing a sweater. I ran out of time in the first segment, so I wasn't able to continue recording, but now I'm hoping to finish. And where we're at right now is we created our machines. And with the passing of time, I actually posted this article and got some great feedback from people. And I made a mistake in this, and I want to show you the mistake that I made, and we're going to go back and fix it. And it's actually very small. And it has to do with these calling the next random number. I came from some different environments from simulating random data, and it turns out that the next method, the max value, is exclusive on the upper bound. It's not inclusive. So I'm going to go ahead and fix that right now so that this data is actually generating correctly. And one of the other things I'm going to do is actually change this max work difference. I'm going to change that to 2. And the reason I'm doing that is because after making that change, generating some different data, it turned out the problem wasn't solvable based on the jobs and machines that we were generating. So I'm just doing myself a solid. I'm fixing that now. In a later post, I'm going to talk about identifying infeasible models. Infeasible is a fancy word for there are no possible solutions. I'm pushing that off because it's a little bit more advanced, and I want to have more time to dig into that. But I wanted to let you know that, we don't get it perfect the first time, and that's okay. We're all learning. And I think one of the things that I appreciate more than anything else is when someone just gently provides feedback. I'm like, hey, Matthew, your style might be a little off, or I think you missed something here. I so appreciate that because it means a person cares enough about me to help me improve. So if you ever find something that I'm doing in these videos or any of my posts, please let me know. I want to get better. I joke, I want to be good at my job someday. I'm told that deprecating humor isn't landing the way I intended, so I'm not going to say that. I think I'm okay at my job, but I always have room for improvement. And someday I'm going to write that perfect code, and I'm working on getting there. So here we are. We've randomly generated some data, and I'm going to go ahead and run this again and get all of these things loaded up into my environment. I can move this over here to the right panel so it's a little bit easier to see. And as I'm motioning over here, this is where my working monitor is. And so if I point over here, I'm looking over here, it's because that's where I'm actually typing. And so we've created some of these jobs. I'm going to go ahead and look at the machines. Yep, there they are. And look at these jobs. Cool. We got jobs, we got machines. Okay, let's get to work. Now, I am going to show you, I'm going to walk through the same mistakes I made when I first wrote this, so you can see some of the flubs I made along the way. But at this point, we're ready to start formulating the model, and we're going to use the hashar NuGet import, which is, this is, I think, got to be my favorite new feature of F#. in F# 5.0. I also love the string interpolation with the $sign. That's pretty awesome. But this #r NuGet import is just also, it's opened up worlds for me in terms of being able to just play around with things. So let's go ahead and open up flips types, and open flips slice map. Cool. Let's go ahead and run that. And why are you complaining? Okay, I'm not sure why the compiler's complaining right now. I opened it right here. Do I need to like close it and reopen it or something? I don't know. Go ahead and reopen that. Not sure why it's complaining. I'm going to close down all my VS Codes and see if that's the issue. I hope not to be a little obnoxious, but we'll get around it. Okay. It appears the compiler's happy again. So we're back off to the races. Running that through, we're importing flips. And here we go. Gotta open up this other piece here. Okay. Great. Fantastic. Okay. We're building out our model now. Apologies for that short interruption. And what we're going to do is we're going to create a map of job type to the jobs of that type. And that's going to allow us to say like, hey, I want all the jobs of this given job type. And that's going to be useful for looking those up in our formulation. So let jobs for job type equal jobs. And we're going to use list group by. In this case, we want to say job type. If you hear a little squealing in the background, it's my children. Don't mind them. They are adorable, and I'm just rolling with it because pandemic times, you can only control so much. So what I'm doing is I'm creating a map. The key is the job type. The value is a list of jobs of that type. And that's all I'm doing here so that I can look those up very easily later. I also want to create a slice map where the key is the job and the value is the size of the job. And that's going to be useful for summing up just how much work is allocated to any given machine. So let job sizes equals jobs. And we're going to go ahead and, trustial list map, not amp, map, job, and job size. And then I'm going to pipe that into a slice map. Slice maps are a lot like, you could think of them as a map where you can do range queries on the key. And the other thing to know about slice maps is they're kind of like tuples, in that when you say a tuple, you're not actually talking about a single type. You're actually talking about a family of types, because there's 2-element tuples, 3-element tuples, 4-element tuples. In the same way with a slice map, there's a slice map where the key is 1 element. There's a 2-dimensional slice map where there's the key is actually made up of 2 different types, and you can slice along them independently. And there's a 3-dimensional slice map, 4-dimensional, 5-dimensional. So it's a map where you can slice along the dimensions of the keys. So this one, job sizes, is a single-dimensional slice map where the key is the job and the value is a float. So now we got our fantastic job sizes. Now let's create the decisions, which are going to be, do I associate this job with this machine? And I actually did this incorrectly the first time, and I'm going to walk you through the mistake that I made and then how I refactored it to fix it. So I'm going to use a decision builder. which is computation expression flips. And I give them the name assignment. So what this first parameter here is it's going to be the prefix for the names for all of the decisions I'm going to create. I'm going to say for machine in machines do, and then I'm going to say, hey, for job in jobs, it's killing me because I'm making the mistake, Boolean, right? And then I'm going to put that into a two-dimensional slice map. So the key of this slice map has two dimensions. The first one's the machine. The second one's the job. And the value is a Boolean decision, which we are going to say represents a 1 says, yes, I'm assigning this job to this machine. Or a 0 says, no, I'm not assigning this job to this machine. We will come back to this. There's a mistake here. And I think it's part of my purpose in recording these things is for you to kind of see me make mistakes and then identify those mistakes and go back and fix them and what that thought process was like. If you want the unfiltered version of this, just go read the blog post. There's no mistakes there. So first thing I'm going to do is I'm going to create some constraints which say, hey, every job needs to be assigned. Right, pretty straightforward. So I'm going to call these the let job assignment constraints. Cannot spell, but that's totally fine. Constraint builder. And there's another computation expression and flips. It's a convenience thing, and this parameter is going to be the prefix for the names of all these constraints. And I'm going to say this is job assignment. This is really useful if you're actually looking at like the raw model that gets created, but we won't be going there. So I'm going to say, hey, for each job in jobs, I'm going to say the sum of assignments across all machines for a given job must be equal to 1. Okay, so this is where the utility of slice maps comes in, because what I basically said, like, hey, take this slice map where the first dimension is the machine and the second dimension is the job, and I'm going to say, hey, take that collection, give me all the values across this first dimension, in this case machine, but I only want the values in the second dimension that match this value, job. So I'm going to iterate through each of the jobs for each job in jobs, take this kind of slice, this subset of assignments. And then sum is this convenience function that is in flips for working with slice maps, because this is a very natural way to express this for a mathematical optimization person. If you come from a applied math background, this is close to how you talk. And the idea with flips was to create a way that was an idiomatic way to express these problems, to kind of graduate those, graduate's the wrong term, like ease them into a typed world, because they're typically working in Python or some other scripting languages. Like, hey, you know, types are cool, types are okay. And as much as we can smooth that grade for them, that's what we're doing here. So all this is doing is saying, hey, I'm going to create a constraint for each job, which says you must assign the job to at least one machine. Well, you have to assign the job to exactly one machine. That's what this is saying. Cool. We got our job assignment constraints. Now we need to talk about the fact that we don't want machines to be loaded differently. Ideally, all machines have the same amount of work. And so we're going to create some decisions which are going to represent the maximum loading of the machine, like the machine with the maximum loading and the machine with the minimum loading. And we're going to say the difference between those values has to be less than equal to our max work difference value that we declared earlier. So let's create max work. It's the decision, create continuous max work. And I'm going to say it can go from 0 to infinity. and min work, which is a decision, create, come on, create continuous. I'm going to give it the name min work, and it can range from 0 to infinity. Okay, so now I have these two values. One I want to have represent the value of the machine with the heaviest loading, and the min work I want to represent the value of the machine with the least loading. Okay, cool. So now I'm going to create a constraint which says like, hey, the difference between these things has to be within a range. So I'm going to call this the max work difference constraint. I'm going to say constraint create. All right, I'm going to call it max work difference. I'm going to scroll up here a little bit just so I can see a little bit more easily. Max work difference. And that's going to say, hey, max work, which is this decision I declared up here, minus min work has to be less than or equal to the max work difference. And so this constraint says, hey, the difference in these values has to be less than or equal to whatever this value is here. Cool. Now, by itself, this is not going to do anything because right now the solver is allowed to just change max work and min work to whatever it wants. So we need to create some constraints which actually force max work to take on the value of the machine with the heaviest load, and we need min work to have, we need constraints which will force min work to take on the value of the machine with the least work. And the way we're going to do that is two different sets of constraints. One is the max work constraints. And it's going to say, I'm going to use constraint builder, call it max work. And what I'm going to do is for machine in machines. So I'm going to go through each machine. And for each machine, I'm going to create a constraint. And it says max work. So this decision I created up here must be greater than or equal to the sum of assignments for that machine, all the jobs in that machine, multiplied by the job sizes. Okay, let's unpack this real quick. So what's going on here? I'm summing up whatever this is, right? And what this is meant to represent is like the total amount of work assigned to a given machine. Great. Assignments, remember, is a two-dimensional slice map, machine, job. And I am creating a constraint for each machine. So I'm gonna say like, hey, assignments, give me all the jobs. So all the jobs, that's why this all is here, is it saying like, hey, I want everything in this dimension, but I only want the values where this dimension matches this value. So I'm saying, hey, all the assignments for this machine. And this operator here, if you've ever programmed MATLAB, you've probably seen this at some point. It's called a Hadamard operator. And it's basically an element-wise multiplication. So where the keys match, it will multiply the values in these two slice maps, right? And this thing is keyed by job. This is keyed by machine then job. And so it's saying like, hey, I got job here in this dimension, I got job here, so I'm gonna multiply where job matches, right? So the job size times the decision whether we assign the job to that machine or not. And then we're summing that all up. You can think of this as like an inner join in SQL and then summing the column. It's essentially what's going on here. Very cool stuff. It makes expressing this very succinct. So I'm saying, hey, this max work decision variable, decision, it has to be greater than all, like it must be greater than all the machine, the amount of work assigned to the different machines. So somewhere in there, there's the machine with the most work. And this is saying like, hey, it's got to be greater than the amount of work on each of the machines by itself. Cool. And we're going to do a similar thing for min work constraints. constraint builder, min work, good times, for machine in machines. All right. Min work less than or equal to. Now we're less than or equal to. Assignments. Again, slicing across. We only want it for this. We want the assignments for this machine that we're concerned about, but we want all jobs that you possibly assigned to it. And again, multiply by job sizes. Okay. So min work this is basically the same thing that we had with max work, except the direction is different. So let's talk about how all three of these constraints work together. We have a max work decision. We have a min work decision. These constraints, the max work constraints, say that the value that the max work decision takes on must be greater than or equal to all of the machine loadings. The min work constraints say this min work decision has to be less than or equal to the loading for all the machines. Okay, so max work has to be greater than the most heavily loaded. Min work has to be less than the least loaded, right? Now, this work difference constraint says the difference between these must be less than or equal to our max work difference that we will allow. So it's a combination of all these three different sets of constraints that are actually like controlling this behavior. So this is actually going to force the solver to find a solution where you don't have wildly different allocations of work to the different machines. Cool. Now what we need to do is to create some decisions which say, hey, I want to minimize the number of different job types that run on a machine. Okay, cool. So I'm going to create a decision that's meant to represent that. And I'm going to call it like the setup decision. I'm going to say like, hey, am I going to run this job type on this machine? Not job type. And so if I want to run this job type on this machine, it's going to have to be turned on or like flip to a 1. And if I decide not to run this job type on the machine, it's going to be a 0. And if I think about it, I want the sum of those. I want as many of those to be 0 as possible, because that means I'm not running multiple different job types on the same machine. So ideally, if I had 10 machines and each one ran a single job type, the sum of these setups would be 10. Now that might not be feasible based on the jobs that are available, but we'll see. So let me program that out. And I'm now starting to get, I'm approaching the mistake that I made earlier. We'll go back and fix it. Don't worry. But I just want to let you know, like, sometimes I struggle with this a bit. It doesn't come out fully baked. So decision builder, again, I'm going to say, hey, this is the setups. It's the prefix for the naming. And say, hey, for each machine in machines, do for job type in job types, I want a decision, which is Boolean. And this is going to represent, do I run a given job type on a given machine? Cool. And I'm going to put that into a 2-dimensional slice map, where the first key is the machine and the second key is the job. Great. Now I need to create some constraints which force the solver to actually turn these things on when they decide, hey, I want to run this job on this machine. Okay, well, if you want to run the job on the machine, you have to enable that job type on the machine. So I need constraints that represent that. So I'm going to call them the setup constraints. So setup constraints. equal. I say, hey, constraint builder setup required, saying like, hey, if you want to run a job on a machine, you have to enable that job type on the machine. So for machine and machines, do. And for job type and job types, we're going to say, hey, sum. We need to go look at assignments and say, give me the sum of all the job type. Oh no. And this is where I made the mistake. I didn't really make a mistake. I've part of writing models is you try something, you say like, oh, I need to like change my approach. So mistake is too strong of a term. I'm exploring, I'm figuring stuff out, and I've explored and I found like I'm in a little bit of a dead end. So let's look at what's going on here. I want to create a constraint for each machine and each job type, that combination. And I want to be able to sum the assignments for a machine for a given job type. I can't do that right now because assignments is not keyed by that. It's keyed by machines and job. And what I'm wanting to do, so I'm just gonna like leave this here. Like this is problem, right? I'm wanting to say, hey, the sum of that has to be less than or equal to. Let me just give this statement out here real quick, just so you have the full context. Okay. What I'm wanting to say here, I have this setup decision. A 1 indicates you may run this job type on this machine. And a 0 says you cannot. If this is a 1, so for a given machine, for a given job type, if this is a 1, I'm going to multiply it by the number of jobs that are just out there. So 1 times 20 in this case, this left side would evaluate to 20. Let's say I decide, no, you can't run a job type on here. Well, this would be a 0. 0 times 20 is 0. And so this would say, hey, the sum of assignments for that machine, for that job type, has to be less than or equal to 0. You can't run any of that job type on this machine. So that's what I would like to be able to say, but I can't right now because assignments isn't keyed that way. I need to be able to slice along the job type dimension. So I'm going to come back up here and do some refactoring as we do. So for job type in job types, right? So now I'm got 3 different keys. So, oh, missed the do. So now assignments is a 3-dimensional slice map keyed by machine, job type, then job. Okay, well, now we're getting some red squiggles, which are fantastic. I'm gonna say, hey, now we want all the job types for this constraint. The max work constraint, okay, we were going per machine, but all jobs. So yeah, this is still an all. And this is same deal here. We want all the jobs for that machine. So we want all job types. Cool, great, fantastic. And wait a minute. Almost made another mistake. So I'm really glad that I'm caching this so I can talk you through it. Machines, are they qualified for every job type? No. So does it make sense for us to create a decision for every single possible job type for a machine? No, it doesn't. So now we're going to say, hey, for each machine, for each job type that machine is capable of, and we only want the jobs that this machine would actually be qualified to run. So this comes back to my jobs for job type map, where I say like, hey, I don't actually want to iterate through all the jobs. I just want the jobs for this given job type that I'm looking at, that I'm like iterating through. Okay, so let's think about this. Job type. Okay, cool. This will probably work. There's another case that's not covered here that can be a little nefarious, and I don't think it's strictly necessary to handle it right now, but I think it's good practice too. So I am I don't think actually we're fine. We're fine, because what I was worried about is like, hey, are you going to look up a key in this map using a job type that doesn't exist? But because we theoretically could. So again, I'm glad we're working through this. So machines are randomly generated. Jobs are randomly generated separately. In theory, we could generate machines that are capable of handling all job types, A, B, or C in this instance. It is possible that we do not generate any jobs of like type C. So when we go to some machine that's qualified for job type C, and we're iterating through the job types it can handle, this could be job type C, and then we go try to look up in jobs for job type using a key that doesn't exist in there, map is going to blow up saying, hey, key doesn't exist. And that's not what we really want to have happen. What we want to have happen is say like, hey, I'm going to try to look up, and if there's nothing there, I just want an empty list back. Because that's what this is. Like the key is the job type, and the list is, and the value is a list of job. If there's nothing there for that key, I actually don't want you to blow up. I just want you to give me an empty list. Okay, so let's go implement a function for doing that. Module map. And I am going to call it I'm going to call it let try get with did I not? Oh, okay. I'm like looking at my notes, and it's like hiding where it was implemented. So try find default. So this is something that's going to say, hey, I'm going to go try to find a thing, and if it's not there, I'm just going to give you a default value back. So in this case, we're going to have key, which could be type A, default value. I'm just going to type V, and then I have a map, which is A, V. And then I'm going to say, hey, you know what, match, map, try, find, key, and width. And if you find something in there, give me that back. Whoa, definitely not a void pointer. That's like the last thing I'd ever want you to give me. And if it's a none, then I want you to give me the default value. Cool. So this is what I'm going to use for looking up the jobs of a given job type. And this is purely to protect myself against the fact that I might, because of randomness, RNG could kill me. So here I am. So I'm going to say, hey, map, try find with default, try find default. And I am looking up, just make sure I got the signature correct. Okay, so I'm looking up job type. The default is going to be an empty list. And I want you to look it up in jobs for job type. Okay, so what this will do is if we're trying to look up a given job type in this, we're trying to look up the jobs of a given job type that doesn't exist. We don't have any jobs of that job type. It's just going to give me an empty list and everything's going to be hunky-dory. Cool. That was our slight detour. Now I come back to assignments and say, hey, you want to assign a job of a given type to this machine? Well, the sum of assignments to that machine for that job type, all. I'm going to go ahead and close this. If you're going to assign jobs to this machine, you have to turn on the decision to set up that job type on the machine. That's what this constraint is saying. And we want to do that as little as possible, but you need to have this constraint in there to say, like, if you want to do it, you have to turn it on. That's what this is meant to represent. So now we can create an expression, which is a number of setups expression. Just kind of abbreviate it. And it's just the sum of the setups is all it is. And then they say, hey, you know, I'm going to create my objective type now. So min setups objective. Let's say objective create and say min setups and minimize and number of setups expression. So now I have my objective. I gave it a name, the minimum setups. I want you to minimize, and this is the expression I want you to minimize. Great. We're now at the point to where we can like build our model. Great. So model create. And this is basically, we're just going to compose all these pieces together that we just created. So the min setup objective, model, add constraints. So max work constraints. And then we're going to say model, add more constraints. So many constraints. So constrained. Work constraints. Oh no. I know. I got it. Don't worry. Min work constraints. Model, add constraint. Come on, you can do it. So this is the max work difference constraint. And I like to add the constraints in the order I made them above. Makes it a little bit easier for auditing later, but it's all good. Add constraints. Set up constraints. And finally, jobs assignment. And that should technically be the first one. So you got to assign jobs. At least you have to assign jobs to at least one machine. Not at least. You have to assign a job to one machine. You get the fact that the max work value must be greater than the machine with the heaviest loading. You get the min work constraints, which says the min work value has to be less than or equal to the least loaded. You say that the work difference between those two decisions has to be less than or equal to some tolerance. And then you have your setup constraints, which says if you want to run a job type on a machine, you have to turn that decision on. And we want to minimize how much we do that. Great. I'm now going to use some settings. Oh, what? Did I mess something up? I feel like I messed something up. Oh, that would have been bad. Settings. And I'm going to use mostly the default settings with max duration. I'm going to give it a little bit longer just in case. So this is going to be 60 seconds. It won't take that long to solve. Let result equal solver.solve settings model. Cool. And then in theory, we should be able to solve this thing. So I'm just going to go ahead and select that. Select everything, except the bottom. Say, build me that sweet, sweet model. Things are happening. Things are happening. Things are thinking. Now I'm going to say, solve it. Chugga, chugga, chugga. Sweet. I think it's solved. But we need to inspect and see exactly what happened. So I can go ahead and like print this out. Okay, it did solve. So solve result, optimal. But now like this is kind of ugly. Let's create like a prettier printing of this. So what I want to do now, so this is not the most exciting bit. So I'm just going to kind of copy and paste some code that I put together earlier just to kind of print things out for you. You can see this code all in my blog post, so you can go and see it there. But none of this is like special or unique or what's going on. I just wanted to provide you just kind of like a prettier experience of seeing what came out of it. And so you see like, hey, for machine 1, we had assigned job 7, 8, 10. Machine 2, 4, 5. Okay, you can see it. You can go through here and say like, hey, machine 1, you can see that you have a couple of machines with a loading of 5, one with a 7, one with a 6, and that the max difference in loading is 2. So there you go. That's kind of a basic machine allocation problem where we are minimizing setups, but also keeping them evenly loaded. And this is just the beginning. We have a lot of things we're going to go where we're going to go from here. A lot of things that we're going to explore, variations on this problems, different nuances. It's really exciting and it's fun because this problem comes up in a lot of different industries. I'm using the term machine and job, but it actually translates to a lot of different domains. So don't think that this is just restricted to manufacturing. Anytime you have a people or things that are doing work with different qualifications and different jobs or tasks that you can assign to them, it's likely a version of this problem. So I'm excited to meet with you again and talk you through some more code and some variations. But until next time, you have a wonderful day or evening wherever you're at. Thank you very much for your time. Have a good one.